The topic of my presentation is the impact of this outflow on the structure of short GRB jets at large scale. GRB or gamma ray bursts are intense flash of gamma rays less than 2 seconds, followed by a broadband, long-lasting afterglow or radiation. Each event presumably are likely originate from binary neutron star or black hole neutron star mergers. Other scenarios have been proposed, for example, including magnetard or accretion including neutron star collapse. However, they do not change drastically the main picture. Once the central engine is created, the rotational energy of the black hole is transformed into the jet power and its bulk kinetic energy through electromagnetic coupling. Alternatively, annihilation of neutral and anti-neutral pairs emitted from the accretion disk may be a source of power to the gamma ray burst jet. From complex binary neutron star or black hole neutron star mergers, a second electromagnetic counterpart, namely a kilonova, became observable. It is powered by nucleosynthesis occurring within the neutron-rich outflow after a merger. The most prominent example is the detection of GW170817, which not only provide detailed observation of electromagnetic counterparts but also presented significant challenge for modeling. For instance, the unusual rise of observed in the afterglow light curves of the off-axis GRB emphasized the necessity of molecular treatment for this component in modeling. In this work, they study how the outflow from the post-merger disk impacted propagation of the jet. In particular, they focus on two main progenitor types: the outflow originating from the central engine of run after the binary neutron star and black hole neutron star merger. The accretion disk wind profile obtained from the numerical simulation of general relative magnetohydrodynamics curve metrics performed by them. In the analysis, they distinguish each component of the post-merger environment to emphasize the influence of the disk wind outflow on the jet project's properties. They perform two-dimensional simulation in special relativistic hydrodynamics to study the interaction of the post-merger disk wind and the jet at large scale and its impact on its final structure. And they also consider combination of dynamic ejecta, disk wind ejecta, and jet to study jet and post-merger ejecta interaction in large-scale simulation. They describe the interaction between the jet disk wind and the DE secondly, and they discuss two additional models that show the jet interaction without the disk wind contribution. Finally, they present the evolution of the energy component extracted from the jet, cocoon, and wind. These are the results. The interaction between a short gamma ray burst jet and the expanding DE significantly modifies the propagation structure of these jets. The result is emphasize the critical need to distinguish between the components of the post-merge environments, namely a disk and wind and DE. Each component exerts a unique influence on the propagation and structure of the jet. The results reveal crucial difference compared to common models that use homologously expanding wings, and the energy structure that expansion and the expansion of the expelled materials are a consequence of the assumed configuration, namely either binary neutron star or black hole neutron star merger. The results are sensitive to the interaction between the jet, the disk wind, and the DE. This is demonstrated, for example, by tracking the evolution of the chemical composition of the disk wind flow outflow. This element must be carefully managed since its main characteristics are sensitive to engine properties such as spin, magnetic field strength, and the neutrino cooling. Since the disk wind's contribution to potentially affect the final jet structure, the property of the central engine will be reflected in the estimation of electromagnetic powder parts.